I have a paper I've been meaning to write for a long time. I work on this plasma physics phenomenon called plasmoids, and I think it might explain UFOs.
Do you think the buzz around astrology has been positive or negative for the field of astronomy?
Ooh. It certainly makes for a lot of fun takedowns. We get to disprove astrology stuff.
Hello everybody, welcome to the third episode of Dan Loves to Chat. My name is Danielgeneen. I am a comedian. I worked at Eater for a long time making videos about restaurants. On today's episode, I am very excited to have my friend Drummond Fielding. Drummond is a newly minted professor of astronomy at NYU, and he is on the show today to explain astronomy to me in extremely simple terms. I know nothing about it. My knowledge of math is weak. My knowledge of science and space are weak. He's an amazing teacher. He's amazing at explaining and being patient. So if you don't know anything about astronomy, I think this is a great start. The things we go into are explanations of what dark energy is and dark matter. Dark matter is what galaxies are formed around, and he will explain that much better than I will. And dark energy is what pushes things in space away from each other. What's so fascinating about these things is we sort of know how they work, but we know basically nothing about them. We also talk about university politics, what it means to be a professor now, the current and future state of academia, and also some fun, silly questions about astrology and aliens and all those good things. If you like this episode, please send it to a friend. I'm very happy to be here doing these, and enjoy Drummond Fielding. So I think the concept here is I know literally nothing.
Okay.
Okay. When you're at a dinner party and you have to explain to someone what astronomy is, what's your kind of one sentence?
Okay. First of all, if I want to continue the conversation,
Yeah.
I'll say I'm an astronomer. Or maybe an astrophysicist. If I don't want to continue the conversation, I say I'm a physicist. And most people are like, interesting. Okay, goodbye. But when I'm saying I want to continue the conversation, and I'm generally will say astrophysicist, and they'll say, oh, really? What does that mean? What do you do? Okay, what is it? The study of the entire universe. Mm-hmm. So from the Big Bang, the whole structure of the universe. And then, as smallest things we really deal with are stars and planets and black holes and stuff like that. I specifically focus on galaxy formation and how galaxies form and how that connects to everything.
What was the thing that you discovered in astronomy that pushed you to becoming an astronomer?
I saw Jupiter with my own eyes with a telescope, and it was photons from the sun bounced off Jupiter, came back to the Earth through the atmosphere, through the telescope, into my eyeball. At that point, I had taken enough physics that I understood, the nuclear fusion in the sun, I understood the photons, and it just, to be a speck of the universe that understands itself as a 18, 19-year-old, it was so romantic and exciting that I just wanted more.
Besides navigation, the North Star, what was the first thing that people used astronomy for?
OG astronomy is the seasons. Right?
Why?
Because that's really the first, that's the zeroth order thing where you need to have some understanding of our place in the universe, right? Because why do we have seasons? You have the sun and the Earth. The Earth is rotating. Mm-hmm. And the important thing is that the Earth is tilted. So it's rotating about an axis that's tilted about 23 degrees relative to the orbital plane. And so in the summertime, it's when the northern hemisphere is tilted towards the sun. And crucially, this explains why it's wintertime in the southern hemisphere when it's summer in the northern hemisphere. And then it goes around, and we're in the winter time over here, and because the northern hemisphere is tilted away and the southern hemisphere is tilted towards the sun. So, I think understanding that it's pretty actually kind of crazy to imagine just being a human before we understood that and how you actually come to understanding that.
Yeah.
Yeah.
What did they think?
I mean, honestly, I have no clue, but the ancient Greeks, they did all kinds of crazy experiments. The ancient Indians, they would, it was sort of a luxury good to have an astronomer on staff as a king throughout all of human history. I mean, even today,
It still is.
It still is.
Yeah.
You know, I get a lot of my funding from billionaires who are interested. And yeah, I mean, I think the experiments they would do a lot of just looking for a really long time. I mean, astronomy, here's the thing. It's fundamentally an observational science. So it's just take as much data as you can. Look at the stars with the biggest camera you have, the biggest telescope you have, or before any of that, just with your eyes, until you start recognizing patterns and try to come up with theories. And, you know, I mean, you know, the Earth orbiting the sun, for example, was a big change in the paradigm, right? Ptolemy thought the sun and everything else orbited the Earth, and then the Copernican revolution was, you know, changing that paradigm. Yeah.
So it's all observational. So like, let's say, you know, giant moon rocks landing on Earth, or if a big ship comes and takes a chunk of Mars and brings it back here, that's not your domain anymore?
Not really. Not really. That's so, I mean, we definitely overlap. Don't get me wrong. That's more in the realm of planetary science.
Okay.
So actually, at Cornell, one of the things that makes Cornell special is that it's a joint astronomy and planetary science department. So a lot of the people there are working on Mars sample return, which you just brought up. You know, they dropped, I actually have no idea how this works, but they like sent a spaceship there, pick some stuff up, and is coming back somehow.
But you'd be brought in to determine like flight paths and things like that?
No. For me, okay, me personally, what I work on. So
No. I mean, as an astronomer?
As an astronomer, we would be brought in to observe all of the properties of the planets themselves. So, I mean, that's where we do overlap with the Mars sample return stuff,
Right.
but also just like, where is Jupiter relative to Saturn? Where is the asteroid belt? Where are all the other planets? And then crucially, where are the planets around other stars? Because fundamentally what we're trying to do is not categorize what kind of dirt there is on Mars, but we want to understand, in this planet example, how planets form, why they are the way they are, and really just like understand the underlying physics behind it. So it's an observational driven field, right? We use telescopes and things to get as much information as we can, but the fundamental goal is not stamp collecting. We don't want just to have pictures of all the planets. What we want is a robust theoretical model, a story that can explain why the universe is the way it is. And so me personally, I'm actually a theoretical astrophysicist. I've never, ever used real data, ever. I find real data horrifying. Instead, I use a chalkboard and computers and try to come up with theories to explain what people see.
Do you ever get proven right?
Yeah. Yeah, I think so. Where, that's a good question. I thought you were going to say ever get proven wrong. Yeah, I think we've got some pretty good evidence that I was right once.
So what's it like in simple terms? What's something that you would project? Like, what's a hypothesis that you have?
So what do I work on? I work on, I said this before, galaxy formation. Let's just say, what is a galaxy first? Galaxy is a collection of stars. Our galaxy, the Milky Way, you know, it's really dark at night. You see the swath of white stars with some mottled brown, which is gas. The brown is gas, and the white is stars. There's about 100 billion stars in our galaxy. And there are about 100 billion galaxies that we know of. And they're really, when we look out and we want to understand the whole structure of the universe, they're the building block of the universe. They're sort of the biggest bound structures. And so when we look out, they're They're the nodes of brightness. They're the big luminous objects. So they're really what a huge fraction of astronomy is about, and connecting to cosmology and understanding the structure of the universe. So we got to understand how galaxies work if we want to use them to understand the structure of the universe or the formation of stars and planets, which all happens within galaxies.
This is maybe a dumb question, but how does the grouping of a galaxy work? Like, are you drawing borders kind of like we do in countries?
Great. No, they're very, very distinct.
Can I guess?
Yeah, guess.
My thought was always that it was in the similar. Okay, this is so stupid. But like, if you think of a tin roof,
yeah,
you think of something sitting on top of it, like a
Yes.
sphere sitting on top of a tin roof.
Yeah.
If these are two galaxies,
Yeah.
this sphere would not be in either one. But like, it's whichever gravity it's affected by most, that's the galaxy that it's
yes,
in.
100% right.
That's right?
100% right.
Wow, what?
Yeah. You're a budding astrophysicist over here.
Wow. Okay, cool.
Yeah, but it's gravitational binding energy. It's which node of gravity are you bound to, and that's a very cut and dry.
So
thing.
you can have mini galaxies within a big one? Mm-hmm. Cool.
Mm-hmm. Yeah, so the Milky, if you go to the southern hemisphere, you look up at night, there's these two white splotches in the sky
Yeah.
that are the large and small Magellanic Clouds, and those are what we call satellite galaxies. Those are galaxies about, the bigger one is about 1/10 the size of our galaxy, and the smaller one is about 1/50th the size, and they're both sort of on their way. They're that ball on the tin roof, and they're rolling down. They haven't reached the bottom yet, but they're on their way in, and eventually...
The tin roof doesn't really work because, as a full analogy, because they would just go right to they'd all go to the same place.
Yeah.
But anyway, sorry.
Well, no, but okay, so let's stick with that for 1 second. Imagine you had, instead of a tin roof, let's say like a bowl, a big bowl, and you put a marble on it. And if you put the marble just on the edge and you push it in, it will go straight through the center,
right,
like you were saying on the tin roof. But if you give it a tiny bit of motion to the side, then imagine what's going to happen. It's going to fall in, and then it will kind of orbit.
Right.
Right?
Okay.
And in galaxies, there's no friction.
Crazy. So is it maybe true that a lot of planets or a lot of stars, planets that are on the outsides of the galaxies are actually affected by other gravitational fields, and that's what's keeping them kind of further away from whatever the center core is?
Okay, they are definitely more sensitive. The farther away you are from the center, the more likely you are. It's called tidal stripping. You get a lot of, if another galaxy comes by, it's more likely to strip away the outskirts.
Got it.
But it's actually just where a star settles, whether it's close to the center or is out in the outskirts, really just determines, if we go back to that bowl analogy, how much initial sideways motion it had. Because the angular momentum, which is the orbital energy it has, is conserved. So if you have almost no horizontal motion, then you settle near the center. And if you have a big one, you have a large orbit, right? And if you have too big, you just fly out of the bowl.
Yeah.
And then you go into some other bigger potential well.
And that's what you see in all space travel movies. They call that the slingshot, right?
Slingshot, exactly. Yeah. And this is true. Yeah, exactly. So you're fully on. So
fully on. Yeah.
This is true for the gravitation of our, Earth, and you can slingshot off the Earth. It's true for our whole solar system. It's true for the whole galaxy, and then whole big clusters of galaxies. Gravity sort of works for the most part on this in the same way on all these scales. Yeah.
Okay, so that's galaxies.
Good. So that's galaxies, and So
galaxy formation.
Yeah. So what does it mean for a galaxy to form? It's kind of a bad name because they're continually forming. They're always growing, and what it means for a galaxy to grow really is some gas flows in to the galaxy. and forms sort of psychedelic fractal clouds like you've probably seen from the Hubble Space Telescope and James Webb, all these like beautiful, crazy, the pillars of creation and the Horsehead Nebula and all these crazy gas clouds. Those crazy gas clouds are in the process of collapsing to form stars. So their gravity is winning out against the sort of thermal pressure, and they're collapsing, and eventually they get so hot in the inside, they start to fuse hydrogen into helium, and they form a star. Okay, so that's really what we mean when we say galaxy evolution, galaxy formation. It's the process of giving fuel for ongoing star formation. You can have collections of hundreds of millions of stars, maybe even a billion stars. That's not a galaxy. And the distinction between the two is this stuff called dark matter. So galaxies are gas, stars, and dark matter. And if they don't have the dark matter, we don't call them a galaxy. We call them generally a globular cluster or something like that. And that's part of a galaxy, a constituent. So
with no commitment.
No commitment.
And what's the dark matter?
Yeah, that's the real question. So if you want to break down astronomy right now into like what are the deep, biggest questions, which most astronomers probably don't even think about because we're so like caught in our little nuanced piece, our little niche that connects to this larger big question, I would say there's two. What is dark matter? And what is dark energy? Both of them have really remarkable names, dark energy.
Yeah.
They're very remarkable in how sort of lacking of creativity we are. And they're dark because they don't emit or scatter light, and we are in the dark. We have no idea what the heck they are. So dark matter is extra gravity. When we look at galaxies, they seem like they have too much mass. We can look at a galaxy, we can see how bright it is. The brightness comes from stars. Okay, we know roughly how stars work, so we can say, all right, with this much brightness, there must be this much mass. And when you have a certain amount of mass, that tells you how fast something should orbit. So the gravitational potential energy is what determines how fast things spin. So the more mass you have, the faster you spin. And when we look at galaxies, they're spinning really fast, like many times faster than they should be spinning. And so people are like, there's this extra missing mass.
And you're determining that by, in simple terms, the amount of brightness.
The amount of brightness relative to the rotational velocity.
Right. That's what I mean. Yeah. So it's like, wow, there's not a lot of brightness, and those things are flying.
Exactly.
So there must be something else there.
Exactly.
Okay.
Exactly. And, people thought, okay, maybe there's lots more gas. The gas could be invisible. It could be transparent, right? Or that didn't really work out. So maybe there's tons of little black holes, and that kind of got ruled out. And there's a whole huge industry of people trying to come up with models that might explain this. And now people are leaning more towards a different kind of actual fundamental particle. So this is where the more physics side of astrophysics comes in. And there might be a different part, not an electron, not a proton, not a neutron, some other kind of particle that there's actually about 6 times more in the universe than there are of us, normal matter. And that dark matter, if there is something like that, and it behaves exactly like normal matter when it's talking about gravity, but it doesn't ever interact with itself or interact with other particles. So it just kind of like whizzes through us at all times. It doesn't bounce off. I can't put my hands through my hands because the particles bounce off each other and interact. Well, with dark matter, it behaves sort of like a ghost. it can pass through. Or if it does scatter, it scatters only a tiny little low probability chance. Okay, fine. Maybe that's getting in the weeds a little bit, but
No, that's so interesting.
yeah, that's dark matter, and that's
What are some ways that that dark matter could get the galaxies to move faster?
yeah. So it's really just that they form this like, okay, going back to the bowl analogy, the dark matter, it is the bowl.
Okay.
It is, or here's another good one. Imagine you have a trampoline, okay? And you put a bunch of sand on top of the trampoline. And the sand is us. It's normal matter. It's what we call baryonic matter. It's protons, electrons, that kind of stuff. And then you put a bowling ball in the middle of that trampoline that has a thin layer of sand on it. You know what's going to happen, right? It's going to make a big dent. And then all the sand is going to slide into the center. Okay? And so dark matter is that bowling ball. It is extra gravity that pulls everything in and holds it in, right? And now, as that sand comes sliding into the potential well that's made from the bowling ball, it's going to fly in pretty fast because there's a big, fat bowling ball making a big dent, right? And so that's what I mean when I say we look at a galaxy and we see it's whizzing really fast. It's got crazy internal motions. And that's because there's a big invisible bowling ball that's really stretching space-time. It is providing a gravitational potential well, and it's pulling the matter in and causing it to whiz around.
And we don't really know what it is.
No. And there has to be 6 times more of it in the universe than us. We're insignificant compared to dark matter, and yet we have very little idea what it is. Again, let me give you an example. You're inside, it's a windy day, and you look out at the trees. You see the leaves are blowing. You know there's wind, right? You have indirect evidence of something that you can't feel, you can't touch, because you're inside. But you see the wind, right? That's what it's like when we look at a galaxy. We look at a galaxy, the leaves are blowing, man. They're blowing like crazy, and we have no idea what it is.
Because we can calculate gravity.
Exactly.
So the Earth around the sun,
Yeah.
way faster than it should be?
No. The Earth around the sun is perfect. Because, all right, so good. Here's the distinction.
Yeah.
Okay, let's, the dent that the bowling ball makes is really big. It's like a big, wide dent. But if you zoom in close, it kind of looks mostly smooth. And then the individual grains of sand, they also make their own little dent on top of this big dent, right? And so the sun makes its own little dent, and the Earth orbits in that dent really nicely.
Got it. It's only towards whatever.
It's only on really large scales. So that's actually a very extremely important and great question, because there is a characteristic size scale on which dark matter starts to matter. And that's about the size of a galaxy. In the sun and the Earth, we're a tiny speck.
Yeah.
We're literally, okay, let's see, the Earth is 10 to the 13, so it's like, we're about 100, the distance between the Earth and the sun is about 100 million times smaller than the distance from the sun to the center of the galaxy. So 100 million times smaller. The solar system is tiny compared to the huge galaxy, right? And that's the scale in which dark matter works and does stuff. Yeah.
Right, so dark matter is only dealing with solar systems.
It's never dealing with solar systems.
Sorry,
it's only dealing with galaxies.
It's only dealing with galaxies.
It's only dealing with the really big stuff.
Right, okay.
And on small scale stuff,
So solar systems are a joke.
solar systems are a
Low-level
joke.
dealing.
They're really small. No one cares.
Okay.
I mean, some people care. I don't care about solar systems. I work on the big scales, on galaxy scales. You asked me a long time ago, what's something I've been right about, right? You have we now know what a galaxy is, right? It's a big cloud of dark matter, huge, big. It's the bowling ball. It's the dent in the trampoline of space-time. And there's a little nugget of stars in the middle, and 100 billion of them. Most of them have a planet or 10 around them, like ours. Some of them might have aliens. I'm amazed we haven't gotten to aliens yet. Okay.
It seems cliche.
Yeah, I know. But they're pretty cool. Good. So, dark matter, stars and stuff. Okay, so then the question is, how does new gas come into the galaxy and start to form stars? That's a very important piece to understanding how dark matter works. And what I work on is the gas dynamics. And like I was saying before, those like beautiful Hubble images of crazy swirling clouds and things like that. And so where does that gas come from? And what happens to it once it forms stars? In particular, once you form stars, stars are, spoiler, really hot. And so they heat up all the gas around them, and it kind of blows it away in a wind. And sometimes the stars, really big stars, they live for only 1 million or so years, and then they explode as the biggest explosions in the universe, known as supernovae. And these supernovae are like huge bombs. Actually, we use the same simulation codes that were developed to model nuclear bombs on the surface of the Earth to model supernova explosions in outer space. Mm-hmm. Exact same physics. Launches gas up out of the galaxies. And boy, this is, as I say this, it's really niche.
That's all right.
It's really niche.
I'm on it right now, so
okay.
I feel like...
So gas comes in, stars form, stars blow up, they launch shit out. Great. Now, when they launch stuff out...
It's really fun watching you have to high school level really intricate information.
We're not at high school yet. We're in middle school. No. When this wind comes flying out of the galaxy, what is it? It's about 1 million to 10 million degree gas flying up out of the galaxy. It's really hot. So it's actually emitting X-rays. Sometimes we can see those X-rays with special telescopes. But as they fly out, they also sweep up and entrain other stuff in the galaxy. So like you have this bomb go off, and there's a cloud here, and it hits the cloud and kind of shreds it and accelerates it and flies it up out of the galaxy. And the thing is, the X-ray hot gas, really hard to see. But those clouds... are really easy to see comparatively. Okay, we're almost there. So I developed a model for the way the hot X-ray gas sweeps up and accelerates the cold clouds based on fractal, turbulent, crazy mixing layer stuff. We can talk a little bit about it. But really, it's just there's a bunch of small-scale physical processes that I came up with a pretty simple model for that's actually relevant to the clouds in Earth's atmosphere. Like when it's a windy day and the wind is blowing by a cloud, the non-cloud air and the cloud air mix and interact with each other, and the ability for the wind to change the cloud depends on that interaction and the surface area of the cloud. And so I made a model for that. I made some predictions for that. And it looks like, now that was about 5 years ago, and it looks like the new data that we have coming in is really only consistent with theoretical models if you include
some of that little research.
My little piece. Yeah.
Oh, that's awesome.
Thanks.
So is wind going through a cloud useful in terms of thinking about dark matter?
Yeah, so it is in a sort of long convoluted chain, but I have to put that convoluted chain at the front of any proposal I'm ever writing, because everything has to sort of boil down to the big questions, right? What is dark matter? What is the universe? Stuff like that. And so this niche question doesn't necessarily...
Oh, can you give me an example of, is there any research that you've seen getting funded that was kind of designed or was built around like a very pop culture concept, but was actually secretly incredibly niche and like not useful at all in understanding the way the Earth works?
Oh boy.
Like, do people Trojan horse their...
That's all we do.
Yeah.
That's literally all we do. I mean, all of us, we just...
Like, you're looking at fractal clouds,
Yeah.
but you come like, what if Buzz Lightyear was on a trampoline?
I mean, yeah. But all right, we don't have to dumb it down that much for our grant proposals, because most of the people reading the grants are...
Ideally in your field.
Exactly, or at least close enough. However, you know... When you go to Congress and the Appropriations Committee, I know some of the people who interface there, and they're the ones who really have to do the juggling and the acrobatics. But there's enough level of bureaucracy between us.
I want to get back to dark energy in a second, but quickly, can you explain how the grants work, right? Like, now you work for NYU.
Yeah.
You're a professor at
Yeah.
NYU. It's not just NYU that pays for you to do something.
No,
so could you just like, even in a simple form, say I have an idea for this, I go to NYU. Do you go to the board at NYU or something? Like, how does that...
No, it's a great question, and I'll say I've been a professor for all of like 18 months, so I'm fairly new to it. Although I was on the receiving end of my advisors' grants and things before this, so I have a good idea how it works. But basically, I get paid to teach. Or that's like 30 to 40% of my responsibility. The other remaining piece is sort of funding my research group and doing the research. So I gotta pay graduate students and postdocs. Postdocs are sort of like in between a graduate student and a professor. And to get this funding, really what I do is, I tell NYU and they help me because they've got to administer the grants.
And they're incentivized. They want you to be doing dope shit.
Oh, yeah.
Because it puts them on the map.
Well, and they take 58% of my grant.
Oh, really?
Yeah, I'll explain. So there's an overhead, right? There's all these administrators in the university, and they make the university work, honestly. And like, when I have any questions, I have 5 people to ask, and it's honestly fantastic. I don't have to think about it. And my administrators, especially at NYU, are fantastic. And it is a huge university. There's like 60,000, whatever, and they're great. And they cost a lot of money. And so the university, whenever anyone gets a grant, they care that we get on the map. They want me to win awards. They want, people to want to come.
It's
but
money.
They really want my money. And so I got a grant just recently from the National Science Foundation for $498,000. And I think what I actually needed was $240,000 or something like that. And that was for 3 years to pay for a graduate student, to pay for a postdoc, and to pay me to work over the summer. Because I only get paid for teaching, which is 9 months a year. And then the whole rest of that money goes to the university, goes to pay for the overhead. And
of course, it goes to the kitchen that you rented to do your cooking in.
Exactly. It keeps the lights on. It does all of that. I think, I actually should know this, but I think tuition is smaller of an income source than all of the research grants and taking the overhead on that.
Okay, so then let's say you put together, so you had this grant, and then you have to are you finding independent sources? Are you finding...
Yeah,
So you're like approached as a potential, because it's not easy to get the job that you got, of course. And so is that something that's like your access to funding? Is that something that's discussed? In when
so getting tenure.
Yeah.
What I think it comes down to is, can you bring in money? And I got to be a good enough teacher. I love teaching. I'm a good enough teacher. I got to publish some papers. I got to actually be doing research, but really what they care about is, can you bring in grants? And so when I'm going through this application process, like getting the NYU job or before that getting the Cornell job, they look at who's doing research that's interesting. And by interesting, that is also then reflected by who are the people getting grants. So the kind of work I do is interesting right now. And so funding agencies are funding people doing my kind of stuff, and I work on a lot of different things. So if one field sort of dries up, I can easily focus on another thing. And so I go primarily to the National Science Foundation and NASA to get funding, some Department of Energy stuff, because some of my work interfaces with like fusion. So I do a lot of like plasma physics stuff, and so there's overlap with fusion reactors. And then there is private money. Private money, I'm a little less. Some people really know how to get it.
You'll figure it out.
But I did get one big one, so I'm happy about this.
You hear a lot that academia is fucked.
Yeah.
Because a lot of, you're a physicist, a lot of people who would be in the field of academia there just isn't the money there that they would get from from working at OpenAI or open at, at a quant hedge fund or quant trading firm or back in the day at like a regular bank job or So what, how is that changing, or is that?
It's definitely not changing. It's maybe getting, it's as bad as it ever is. If you want to, I don't know. It's an excellent point. I mean, one of my best friends from graduate school on October 1st, just a few days ago, started at OpenAI. I think his total compensation in his first year is going to be $2.2 million. I don't know how many decades it'll take me to earn that as a tenured faculty at a great university. But, none of us do academia, physics in particular, for the money. It's honestly, it's a great career. It's a good life. I make enough money. I get to travel the world to go to conferences and stuff. I'm certainly not hurting. But there's a huge scarcity of jobs. And, the number of people who, get a physics major and then are able to get into grad school, that's already a huge hurdle. You're trimming away 90%. And then getting from physics grad school to a postdoc, that's another huge hurdle. And then, at the NYU job, there's probably 200 applicants who all had PhDs, who everyone is super, super good. And it's just the tiny luckiest people or whatever best people who actually get a job. And the rest all leave. And most of them go make a lot more money. But it is...
And also some of them get peeled away throughout that process.
Oh, yeah.
Because why subject yourself to such a depressing, almost lottery, not quite a lottery, when you would get that offer from OpenAI for 2.2 or something like that?
Yeah. I mean...
Sure.
Danny is exceptional. And, that is not an average...
No, but I imagine the top 20 candidates who applied for your job at NYU would all be have enough of a physics background that at least one of these quant-based trading firms or something would be like, we'll try you out.
Yeah, definitely. Probably, I would say the quant firms, definitely. A lot of people, especially being in New York, a lot of the people who sort of bow out of academia go to one of the big
you got to hope that a lot of those people in your position, someone that's sick or you need the money. I mean, it's just, so what is in a perfect world, how would the sciences attempt to keep some of those people away from going into finance?
Yeah.
Is it just...
Okay, I applied for finance jobs when I was nearing the end of my postdoc, and I was telling myself I was never going to be the lucky one, the one who gets picked. And so I almost didn't even apply for any faculty jobs. I was like, it's a foregone conclusion. I won't get it. I'm not going to subject myself to this. Let me just go apply to some quant funds. And so I interviewed at Citadel, went super well. It went better than I expected. So they brought me in for an on-site, and I actually was like, no, let me apply for faculty jobs first, because this was actually...
Because you're like, I didn't realize how smart I was.
Exactly. I didn't know that this would even be... I thought I would get
Citadel, for those who don't know, is a top 5 quant trading
like
firm. And quant stuff, for those who don't know, is basically stock trading with a lot of odds-based physics and algorithm creation.
Yeah, it's nerds. It's math. There's traders who use like their intuition and their gut.
Who's like, I got a good feeling about Ukraine.
Exactly. And then there's
quants when the weather in Ukraine dips below X temperature, people rely more on coal, and when people are buying more coal, they're actually not using as much, they're not fishing for as much salmon.
Exactly.
So we're going to short sell salmon based on
whatever. The weather report says this. Yeah, exactly. Crazy signals.
It's sick though.
Yeah, it is really cool. It's cool. It is really cool. And I mean, I think it would be super fun. It's like good, hard problems, and it's why, the true unifying factor of all physicists is that we love a good problem. And a lot of us are driven by this like romantic beauty of trying to like solve the universe, whatever. But when it really comes down to it, it's just like
fix a problem.
And it's really cool. And we, so many astronomers love
on it.
Exactly. A lot of astronomers love like board games and puzzles and stuff like that because it's that muscle
and gambling.
Yeah. Yeah.
So if there was more money, though, if there were more jobs, that would be better.
Yeah.
If there was more money available for research, right? Like, I guess would it be fair to say that you could track the quality of academic progress by charting the amount of money that was available for grants?
Yeah, I think so. Definitely. And because if there's more grants, it's not just I get to hire more grad students, the university would get to hire more faculty. And I think that's really the key thing. It's the endpoints. Because there are tons of physics and astronomy majors being cranked out every year. A lot of them are really good. Some of them don't have on paper everything what they need to get to a graduate school. And so they leave. And if there were more professors, then there would be a bigger demand for grad students, and these students would maybe have a chance. And most of the ones would probably crap out and wouldn't do so well. But by casting a broader net, you'd have people, you don't know who's going to peak. Like, I didn't have my best idea until I was 5 years into a postdoc. And, and hopefully I'll have more good ideas later. But
you're only as good as your next one.
Exactly.
Interesting. So you think in a perfect world, Dick, there'd be more space for people who were, especially like people who were not good schmoozers.
Yeah.
Right? Like, I imagine you are good in grant proposals. You're good in the room.
Exactly.
But I bet there's a lot of astrophysicists who are not fun to talk to.
Yeah, and it's actually interesting.
And maybe they're brilliant, but they can't.
And I would say most professors are actually fun to talk to.
Right.
Because we're the ones who have survived this far.
Yeah.
And
you have to be not only brilliant, but also you can raise money.
Yeah, and play the game. And, network and do all that stuff. And it's a bit of a pity that science isn't just this pure thing. And there's a lot of resentment, I know, among people who don't end up getting a job, that in order to get a job, you really have to play the game. But we're humans. And we are in a capitalist society, and it's just fundamental. And I think having generally more would allow for some of the best technical talents, because you don't have to play the game at a quant fund. You just have to make money, and if you make money, you can be the weirdest motherfucker in the world, and not and so that's where I think they're scooping up a lot of excellent talent that isn't staying in academia.
What's dark energy?
Okay. So this is a fun one. All right. First of all, have you heard of the Big Bang?
Yeah.
All right. Universe, we have no idea what happened before this, but for some reason...
Our universe.
Okay. Well, the universe is a definition. It is everything. Now, there is a multiverse thing where you can have separate mini-verses. I don't know what the word is, but that bounce off each other and shit like that. We're not going to deal with that. So the universe comes into being. Something happens. God says, "Let there be light." Whatever. There's some thing that we have yet to understand, and the universe is super high energy density. It's very, very unbelievably hot and incredibly tiny. And the universe expands and gets bigger, and as it expands, it cools. And eventually it cools enough that, protons can form. And then it cools even more, and protons and electrons can bind to each other and form hydrogen. And then the universe becomes transparent, and then things form, and then the hydrogen and helium and other elements collapse and form galaxies. And that's sort of the history of the universe, okay? Big Bang, stuff cools, it gets bigger and cools. All right, now what is not obvious, though, is what is going to happen far in the future. So the universe gets bigger and bigger and bigger and expands, and you could sort of maybe imagine that it would collapse in on itself again. And for a long time, that's what we thought was going to happen, this theory called the Big Crunch, where the universe is a little speck, and it goes, and then it collapses in, and then maybe it would repeat, and it would be these repeated cycles of,
Would it be getting slightly smaller every time?
No, because all energy would be conserved.
Right.
Because it's everything. You'd need. It would get smaller if there was friction, if there was dissipation. But if it's everything, then there's nowhere for that energy to go, and so it's.
Got it.
It would just sort of continue like bouncing forever. But when we look at the universe, we actually see that the universe, we can see sort of where we are in the history of the universe, and we're actually right at the point where it seems like we should start to collapse again. But instead, we're actually getting bigger, and we're getting bigger faster. So if let me change, so now we're going this way. There's the Big Bang, and it's getting bigger, and now we're instead of coming back down, we're getting wider and wider. And this is really, really, really strange. My former professor, Adam Mise at Johns Hopkins, although he did this work when he was a PhD student at Berkeley, won the Nobel Prize for discovering this, the accelerating expansion of the universe. And if you add up all the extra energy you would need in order to make the universe expand, that is dark energy. And it's this mysterious force that is causing everything to expand away from each other. And it's really weird. And
could that be dark matter?
No. So it actually acts like anti-gravity. So, all right, what does gravity do? It pulls things together. Well, the way the universe actually works, the way we've observed the universe to work, is when you get far enough apart, you start to get farther apart. Normally, you'd think without any dark energy, it doesn't matter how far apart you are, eventually you'll come together. Because gravity is just going to pull. Fine, when you're really far away, it'll be slow, and then you get closer and you'll finally collide. That is not the way the universe works. And it's really weird. There is anti-gravity. There is a repulsive force that acts on really large scales. Everything else we know is stronger when you're closer together. But if you view dark energy as a force, then it's actually stronger the farther away you are. It's really insanely weird.
Okay.
And so let me just give you some of the classic ways of understanding this. There's some normal analogies, okay? So we're talking about the universe expanding. So before I said the universe was a trampoline, now let's say it's a balloon. Okay, so imagine you have a balloon. We draw a little picture on it, me, you, and then we inflate this balloon. What's going to happen is the surface of the balloon is going to get bigger, and the two little drawings we just put on it, they're going to get farther and farther apart from each other. They're not moving relative to the surface of the balloon, right? The balloon itself is just getting bigger. So the distance between them is getting bigger without them moving, which is a very strange thing, right? And if you then put a bunch of little drawings on the surface of this balloon, and you ask, how fast is everything moving away as it's inflated? Well, the dots close to you, they're only moving pretty slowly as the balloon gets bigger. The ones on the opposite side, they've got to move, right? They're moving faster. And so this is what Edwin Hubble did in 1921, I want to say, where he looked at all the galaxies he could find and asked, how fast are they moving relative to us? And he found that they're moving faster the farther they are. And the only explanation for that is that the distance between us is all getting bigger. And so this is...
So there's constant growth of something.
Yeah. Of nothing, actually.
Yeah.
No, it's so hard to wrap your head around. It's the distance between everything is getting smaller. It's getting larger over time. Now, there's something really important, though, is that on small scales, gravity still wins. Okay, so within a galaxy, and now I'm saying galaxies are small, but within a galaxy or within a solar system or in this room, gravity wins. So we're held together. But, opposite sides of the tin roof, like you were saying before, the bottoms are getting farther away, even though inside they're staying the same. Does that make sense? So
it's like in the no man's land is
the
growing.
no man's land. Exactly. So another classic example is, say you're baking some raisin bread. So it's the loaf of bread is growing. The loaf of bread is the universe. The galaxies are the raisins, and the dough is just the firmament, it's space-time, right? And as you cook the bread, it expands. And so all the raisins move apart from each other. Although maybe chocolate chips. Better.
Jesus. All right. I got to ask you some.
Okay.
Okay. So I just want to wrap up with a few kind of closer or quicker questions. Working in a university, do you ever get excited about the more like conspiracy side of astronomy and aliens and stuff like that? And do you feel like some level of pressure not to speak about those things until they become facts or like to...
No, I mean, I don't feel any external pressure. A lot of times it just feels like noise and I'm not really interested, but, if all press is good press. And so, especially if we can maybe educate the public a little bit and actually like lend some real hard evidence to these discussions, then I'm all for it. And I think the university would be too. A lot of my colleagues... get interviewed by New York Times for things like this. I have a paper I've been meaning to write for a long time. I work on this like plasma physics phenomenon called plasmoids, which, we can talk about next time. And I think it might explain UFOs.
Really?
I'm a little bit afraid to write the paper because I think I'll catch a lot of heat from, the people who love UFOs and me saying it's just a ionosphere bubble of magnetic fields that can move in really weird ways and refract light in weird ways. And I don't think it explains everything people have seen, but I think most of them are atmospheric phenomena.
I hate to give the most simple perspective on UFOs of all time, but I just think that like not to project any kind of worldly intelligence on them. But if they're capable of teleportation, dancing around, and all that kind of stuff, it's like they're not getting caught. You know what I mean? Like they're not. If they get caught if they wanted to get caught.
Yeah.
I just think oops, we accidentally like. Do you think there's some stoner up there who like turns off the invisibility cloak for a second?
No, and who lands in a cornfield and. No way. Do
you think the buzz around astrology has been positive or negative for the field of astronomy?
Ooh. Yeah, positive. It certainly makes for a lot of fun, like, takedowns. We get to, like, disprove astrology stuff. But
how do you disprove astrology?
Well, okay, we did this in one of my classes I taught where everyone had to read the daily horoscope, but they didn't know which sign it was contributed or describing, and so they read through. They picked the one that best described. It was at the end of the day, and this was supposed to have described their day. So they picked the one that best described their day, and then we compared how many people got it right, and it was a big class. There's maybe 400 people. It was almost exactly 1/12. Which means random.
Yeah, but that's a real Scorpio thing for you to say.
Oh God, oh boy.
What are annoying jokes that people make to you about astrology? Finding out you're an astronomer.
I mean, most of the time, it's just every, you know. When I say I'm an astronomer, going back to your very first question, when I say I'm an astronomer, I get one of two responses. They say, "Oh my God, I'm a Virgo," or they say, "I loved Big Bang Theory." And that's 90% of the responses.
Pick your poison on that one. What is one thing you can say to people about astronomy quickly without them having a lot of prior knowledge that will gobsmack them?
Excellent question. Okay, maybe every single grain of sand, every single piece of your body, every single piece of everything you've ever seen was formed inside the 100 million degree furnace in the center of a star. But not just once. Your atoms have been reforged at least 3 times, where a star formed, it turned a whole bunch of hydrogen into heavier elements, then blew up, polluted its surrounding neighborhood, reformed, blew up, and all of us, everything you've ever known is, you know, to quote Joni Mitchell, stardust. And it's, I don't know, for me, it's remarkable that you know, it feels so distant and so arbitrary, and yet it is what we are. I don't know about gobsmacked. That's a good question. I need to have more of those.
I just mean, like, if you were like some girl in an elevator or something, they're like, "What does astronomy do?" or whatever, like that. I just, for me, it was a little bit of that dark matter stuff. That's what really started to fuck me up.
Yeah, that we don't know. Okay, we don't know what 95% of the universe is. It's kind of fun. 95% of the mass and energy in the universe, we have no idea what it is. We know that we don't know what it is. We know that there's something we don't know. About 75% of the universe is dark energy. No idea what it is. 24% of the universe is, no, 22% of the universe is dark matter. And then the rest is us. We're insignificant. We're a rounding error in the universe, and we have no idea what the rest of it is.
And astronomy is just trying to increase our percentage of the known.
Exactly.
Every day you get a little bit.
Every day we hope to get a little bit.
So when people say, like, who knows what's in the ocean? There's so many parts of the ocean that are unexplored. You're like, the ocean's nothing.
You don't even know. Although it's a good question. I like see those like clickbait headlines all the time. There's less known about the deep ocean than there is the surface of Mars. I don't know what what fraction it is, but I think like astronomy, we blow them out of the water.
Yeah. All right. Let's get out of here.
All right. That was fun, Dan.